In this slide we explore what the signals at the different stages inside the op-amp looks like, with a double pole added. The ideal op-amp circuit with a double pole is shown again in this slide. The first signal to look at is the voltage after the first amplification, E gain. The second signal is the voltage after the first pole. The final signal is the output signal after the second pole. We are going to explore what all three these signals look like in both the frequency and time domains. In this and the next two slides, we explore what the signals look like at the various stages inside the op-amp, with a double pole added, when the frequency of the input signal increases. Let's refer to the double pole op-amp schematic, so that it is easier to follow. This is what the three signals look like in the time domain. The input is a 100 mV, 100 kHz sine wave signal. It is clear that there is no phase shift between the signals at this frequency. The red curve shows the amplified voltage at the input to the first pole. The green curve shows the voltage after the first pole. And finally, the signal after the second pole is shown in purple. This is the output of the op-amp. There is no visible phase shift between the signal after the second pole and the first pole. This is because the poles are quite close together, at 10 MHz and 20 MHz respectively. In this, the second slide of exploring the phase shift between the internal signals of the op-amp, we explore what the signals look like at 1 MHz. Let's refer to the double pole op-amp schematic, so that it is easier to follow. This is what the signals look like at 1 MHz. There is slightly more of a phase shift between the signals at this frequency than before. Also note that as the phase shift increases, a small attenuation appears. The input signal in red has a slightly higher amplitude than the other signals. The red curve is the amplified input signal at the input to the first pole. The green curve shows the voltage after the first pole. The purple curve shows the voltage after the second pole, which is the output of the op-amp. In this, the third and last slide of exploring the phase shift between the internal signals of the op-amp, we explore what the signals look like at 10 MHz. Let's refer to the double pole op-amp schematic, so that it is easier to follow. This is what the signals look like at 10 MHz. This time, there is much more of a phase shift than before, between the signals of the different stages. The red signal is the amplified signal at the input to the first pole. The green signal is the voltage after the first pole. The purple signal is the voltage after the second pole, which is the output of the op-amp. This is the LT Spice schematics for the single and double op-amp models. The simulation file is attached. It is set up to calculate the time domain response for the first 100 microseconds. The LT Spice schematic is attached, and it is set up to do a transient time domain response simulation of these two circuits. The name of the LT Spice file is shown in the slide. The assignment is to run the simulation and vary the input signal frequency, as well as the values of our pole 1, C pole 1, or pole 2 and C pole 2. This brings us to the end of the analysis of adding finite bandwidth to the ideal op-amp. Next, we are going to add closed-loop feedback to the ideal op-amp with finite bandwidth. As we shall see later on, this has implications for the stability of the op-amp. With an ideal op-amp, there are no stability problems, because there is no phase shift between the input and output of the op-amp. We showed earlier that feedback is used to minimize the effective variation in the open-loop gain of the op-amp. But limiting the bandwidth of an op-amp by introducing either a single or double pole circuit does affect the frequency response and stability, of the op amp when feedback is added.